Here I'm going to talk a little bit about recent work in domain-specific training for biomedical NLP and specifically highlight PubMedBERT. And so as we all know, biomedical text has been growing at an explosive rate. PubMed adds thousands of papers a day and over 1 million a year. And curating knowledge from all this paper by hand is obviously very challenging. Similarly, the advent of electronic medical record make it available all those high definition longitudinal patient information. But unfortunately, the bulk of this information reside in the free text, such as clinical notes, and curation is very expensive and time consuming. For example, curating basic information for a single cancer patient can take hours. And in the US alone, there are close to 2 million new cancer patients every year. And curating them all, obviously, is hard to scale. And so this has motivated us our biomedical NLP research agenda, where we have been focusing on developing machine reading technology to help unlock knowledge from text. From literature, we can aim to extract PubMed scale knowledge graph of important biomedical entities and relations. And from electronic medical records, we hope to extract population level real-world evidence that can help drastically accelerate clinical research and improving clinical care. So this all sounds good, but unfortunately, the standard supervised learning paradigm obviously require a lot of training data. And that has become, annotating all those label examples have become a major bottleneck. Self-supervised learning offers an alternative paradigm that can help alleviate this problem. The key insight is actually very simple. We are leveraging all sorts of self-specified template to trying to essentially hallucinate a very large number of label examples automatically from the unlabeled text. So a particular popular form of self-supervised learning obviously is language model pre-training. And the idea is very simple, right? So given the unlabeled text, we just randomly mask a bunch of words and then ask the language model to try to predict them back. So the hope is that in this way, we can force the language model to try to capture important semantics by modeling the distributional similarity or the co-occurrence of the words. So pre-training obviously has attained spectacular success, but most existing work have been focusing on the general domain, such as newswire and the web. And there is fierce competition in trying to scrape ever larger text corpora to train ever larger models. When we look at biomedicine, on the other hand, the biomedical text obviously is very, very different. But existing work in biomedical pre-training tend to be very simple extension of general domain pre-training. Usually a standard way is to basically piling on additional PubMed or other biomedical texts on top of the general domain models. So the prevalent assumption is that going back is always better, right? So the assumption is that when you have a model that train on more data, that tend to be better than the one that train on less. Now, if your target domain have very, very little data or text in this case, right, then this could make a lot of sense, right? So you hope that the source domain still have a lot of common linguistic phenomenon so that once you capture them, you can hopefully pass on to help the target domain. But when you look at the biomedicine, actually that's not quite the case, right? So PubMed abstract alone have more text than wiki plus book that has been used to train the original BERT. And if you add the full text articles, then you have an order of magnitude more text. And so this has motivated us to explore an alternative paradigm that essentially trying to pre-train from scratch entirely using biomedical text. So this led us to create a PubMedBERT by pre-training entirely from PubMed text. So interestingly, for a variety of biomedical tasks, PubMedBERT and domain-specific training actually confer a very large gain. and actually oftentimes again outperform models, substantially outperform models that are larger and often have been trained on much more data. For example, in the COVID biomedical search, we have tried GPT-3 fine-tuned on PubMed text, which arguably is one of the largest model you could try, right? But somewhat surprisingly, it actually merely perform on par of regular BERT and trail PubMedBERT by a large margin. Similarly, on a variety of biomedical NLP tasks, PubMedBERT and domain-specific training have conferred a significant performance gain. So why is going big not always better? Now, one key reason is the domain-specific vocabulary, right? So if you mix in our domain data, they essentially compete against the limited number of slots in the vocabulary, and that force many biomedical terms actually get shattered into nonsensical subwords, and that makes the biomedical pre-training, like capturing the biomedical specific semantic much harder. Another key reason is that much of those our domain data is actually completely irrelevant for biomedicine. So when you're actually conducting biomedical specific training, then if you initialize with all those general domain model, you actually have to also spend some effort to unlearn a lot of those irrelevant semantics. So here is some real-world example when PubMedBERT outperformed BioBERT, which is quite illuminating because the two BERT actually get trained on is exactly the same PubMed text. But the only difference is that BioBERT is actually initialized with the original general domain BERT. And as you can see that BioBERT will shatter some common biomedical terms like epiphilia and serine into subwords and fail to actually recognize the gene mentioned here within the parentheses. Here's another example in relation classification. And once again, BioBERT shatter the biomedical term agonistic and fail to classify this relation. So not only actually mixing in our domain data, using more our domain data may not necessarily help. Sometimes when you mix in domain data, it may not immediately help either, right? So for example, we try actually adding all the full text from PMC, and actually that actually slightly degrades the performance, right? And from hindsight, actually, it's not that surprising. PubMed abstract already have quite significant amount of text, and the full text obviously is noisier, and it actually turns out it takes a bit longer training to be able to recover and actually get a little bit gain. So we also try to actually look at the task-specific layers. For example, how do you transform the input and how do you featureize based on top of the BERT, right? So we also try to look at those components by fixing the PubMedBERT. And what we find is that self-attention mechanism in the transformer model in BERT is actually very, very powerful in capturing long-range dependency. So therefore, you can actually simplify some of this task-specific layer, and that would make the learning and prediction faster and better, right? So for example, for name entity recognition and relation extraction, a standard way is to actually put in some sort of like explicit sequential modeling. And we find that it's actually with a BERT, you actually doesn't need to do that, right? So instead of doing the standard way of putting an LSTM or other RNN on top of BERT, we find that a linear layer classifier actually is already competitive. And similarly, we find that you actually don't need a very sophisticated tagging scheme for sequential labeling. So a simple just distinguish in and out tokens is suffice. You don't need to worry about like beginning, last, and single token unit, single token entities, and so forth. And on the flip side, you also have to be careful with neural network because they are very powerful, but also they can very powerful in memorizing, right? So for example, if you look back in the traditional feature-based approach, back in the old days when NLP is about feature engineering, right? Then one of the sort of like feature engineering 101 for relation extraction is that you shouldn't use entity ID as your features, right? When you now replace those feature-based model with neural network, then this actually obviously become much harder to guarantee. And if you are not careful, then the neural network can simply memorizing basically the entity tuples, right? So leading to overfitting and sometimes leading to disaster performance degrading, as you can see here, if you just use the original tokens, right? Without any other special things. But fortunately, there are actually many ways to actually counteract this problem. For example, you can dummify the entity, you can add entity marker, and both of them actually work pretty well. So we released PubMedBERT on Hugging Face, and so you can easily find them. And we are very excited to see the community has shown a lot of interest. So to facilitate all this study, we have compiled a comprehensive benchmark that's available in Blurb. And so this span a 13 data set across 6 tasks. So obviously we build on prior work such as BioBERT, BlueBERT, and we try to essentially take a superset of the study of the data set using the study. And as we mentioned earlier, we can also leverage domain-specific pre-training in vertical search. So here's a general recipe we have proposed to essentially bootstrap a vertical search engine, and all you need are domain-specific tags and a domain-specific ontology, both of which are usually easily available. And essentially, you use the domain-specific tag to train the domain-specific language model, and then you fine-tune that using self-supervised QA data set that has been selected based on the domain ontology. So we find that this works really well in biomed domain using the PubMedBERT as well as the UMLS as the ontology. And we released this search engine from Microsoft. So jumping up at the big picture, right? We don't envision biomed NLP can actually automate everything from end to end anytime soon. Instead, we really love the notion of assisted curation that have been pioneered by, for example, Zhiyong and others many years ago. And what we envision is that sort of the sweet spot is actually in human-computer symbiosis, where NLP or machine reading can essentially play the foot soldier to empower a curator to become superhuman. Right. So if you think about the curation task as a sort of a pyramid, then actually a lot of the time is spent on the bottom of the pyramid when a lot of the repetitive tasks is happening. So for example, you got a sort of a giant haystack like 4,000 papers today from PubMed, and you want to get some latest precision oncology knowledge, right? So enumerating all those giant haystack is very difficult, but one key observation is that most of those haystacks actually doesn't even look remotely like the needles that you are looking for, right? So even sort of like noisy self-supervised machine reader can potentially filter much of them out, and then leaving just a few sort of like candidate needles so that the human curator can very quickly validate. So for example, we have applied, self-supervised machine reading to precision oncology knowledge, and without actually using a single label example, we were able to actually get already very accurate extraction, emphasizing on recall and with reasonable precision, right? And so this is a prototype system that we have built. So the curator can come in looking at each sort of like curative facts in context with the provenance, and then they can often determine whether this is the thing that they're looking for within a couple of minutes, and they can finish the curation by clicking a button. And so we work with NCI Designated Cancer Center and have been very encouraged to see that assisted curation does, in fact, can actually empower them to curate much, much faster. We have also been making some promising progress in the real-world evidence front, right? So, for example, for the key cancer attributes such as sort of the tumor size, histology, and staging, we are able to attain very, very high accuracy and start incorporating assisted curation to help speed up the curation. And here, domain-specific pre-training again play an important role. And we actually try to pre-train an OncoBERT using oncology notes because that's still quite different from the general sort of like biomedical literature. And we find that actually in this particular application, right, then actually perform even better than the PubMedBERT. So going forward, there are many exciting directions. For example, there is still a lot of additional work that can be done to improve the task-specific fine-tuning. Pre-training is very expensive and very costly, require very powerful GPU cluster. And can you actually make that learn faster and better? And also, we talk mostly about how do you leverage unlabeled text, but actually there is a lot of room to actually incorporate like domain-specific ontology, the knowledge base, and so forth into the pre-training. So these are all the folks that actually done the work. We also are really thankful to a long list of collaborators without whom obviously we can't do any of this. Thanks everyone, and I'd love to take a couple of questions if there is time.
Sorry, I was muted. Thank you. It was very interesting. So we do have time for a couple of questions. So there's one from the panelists who cannot ask on the Q&A for some reason. It says, what does it take to retrain PubMedBERT with a new ontology? Also, can one provide multiple disconnected ontologies, or should the ontology be one connected entity?
Very good question. So by the standard pre-training actually just based on text. So you don't even need an ontology to do the pre-training because it's basically trying to look at the unlabeled text and trying to model the co-occurrence information, right? So for that, you basically just need to grab domain-specific text. So for example, tomorrow, if you are interested in just like us, right? Like we're interested in oncology, so we grab a lot of the oncology related notes and train the OncoBERT, right? Now, on top of that, as the panelists alluded to, you can also incorporate a lot of the domain-specific knowledge, and that's actually a very exciting sort of open area. And I would say that there is still a lot of open questions to be had there. And also in my talk, I mentioned the vertical search. In that case, then the ontology was used to essentially select sort of like QA pairs that are sort of like specifically relevant to that particular domain to try to fine tune on top of the BERT. So that's sort of like the additional step from the pre-training. So hopefully this answers the question.
Yeah, looks like it. Okay, let me see. I have one more question, quick question from Robert. I expect that using linear layer instead of CRF helps speed up inference, but running a BERT model over all PubMed and PNC still require days or weeks of GPU compute time. Can you comment on your experience with this high resource usage and any ideas on how to mitigate it?
Absolutely, absolutely. This is a fantastic question. So there is actually a very active open frontier where people are looking at, can you compress a BERT? Right. So during the pre-training, you hope to absorb as much information as possible, right, from your domain-specific corpus. But at inference time, especially in some of the use case that actually when you have resource constraint, especially like, for example, when you imagine doing edge computing, right, when you just have a phone or something. So there has been a lot of work in actually, turns out you can actually compress a BERT. into a much smaller size. So for example, we have some internal work where we can actually speed up the inference time by 3 times by simply just using the original BERT to, essentially what's called knowledge distillation to actually train another simpler BERT. So there is a lot of room to actually make the inference faster.